Hello dear students, welcome to Physics Online KCET classes. So in last class we have been discussing about mechanical properties of solid. So in case of that mechanical properties of solid, we got them basic informations related to stress, strain, and we got that relation between stress and strain. So that stress is directly proportional to strain from that Hooke's law, and we got that about that Young's modulus. So in that Young's modulus we got that expression for that Young's modulus. So y is equal to f into L divided by a into elongation. So that elongation is represented by E or delta of L, we can take it. So that Young's modulus for different cases for constant volume. So for different cases we got that expression for that Young's modulus. So in today's class, so let me discuss about that bulk modulus here. So first of all I have to understand what you mean by that bulk modulus. So bulk modulus means it is the ratio of volume stress to that of volume strain. So bulk modulus is represented by the symbol B here. So it is the ratio of volume stress divided by volume strain here. So what is that bulk modulus here? It is the ratio of volume stress to that of volume strain here. So that volume stress is represented. So volume stress is nothing but what? So that is delta of P. So change in pressure. So volume strain means change in volume to that of original volume here. So what is that volume stress here? Delta of P. Volume strain is nothing but change in volume to that of original volume here. So I can rearrange this equation. So minus of V into delta of P divided by delta of V. So this is about bulk modulus here. So we'll consider one more term, so that is compressibility here. So let me introduce that one more term, so that is compressibility. So what is that compressibility? So that compressibility is represented by the symbol K here. So compressibility is nothing but it is that reciprocal of bulk modulus. So in simpler way I can call it is that reciprocal of bulk modulus 1 by B here. So reciprocal of bulk modulus means what? So 1 divided by minus of V into delta of P divided by delta of V here, or I shall rearrange this equation as minus of delta of V divided by V into delta of P. So into delta of P here. So this is about that compressibility here. So in case of that mechanical properties of solid, so we'll understand the meaning of Poisson's ratio here. So let me understand what is that Poisson's ratio. Poisson's ratio. So it is represented by the symbol sigma here. So Poisson's ratio means it gives that information about that it is the ratio of lateral strain to that of longitudinal strain. So what is that Poisson's ratio here? So it is the ratio of, so it gives that information about that lateral strain to that of longitudinal strain. It is the ratio of lateral strain to that of longitudinal strain. So I can call that. So lateral strain means change in diameter, so or change in radius to that of original radius here. So what is that a lateral strain represents here? It is the ratio of change in diameter to that of original diameter or change in radius to that of original radius. So change in diameter means delta of D divided by original diameter. So longitudinal strain is nothing but so change in length to that of original length. So this is about Poisson's ratio. So what's that Poisson's ratio here? So it is the ratio of so lateral strain to that of longitudinal strain, or we can call that it is the ratio of so change in diameter to the original diameter, so divided by so change in length to that of original length here. So now let me consider that what is the relation between, so look at here, relation between volume strain So this one is longitudinal strain, and Poisson's ratio. So after simplifying, we will get that relation between volume strain, longitudinal strain, and Poisson's ratio here. So longitudinal strain is nothing but what? So delta of V by V here. So 1 minus of 2 times of sigma into delta L by L. So after deriving, we will get that equation, relation between volume strain. So sigma means Poisson's ratio, delta L by L represents that. So that is longitudinal strain. So what is that connecting formula for that? Volume strain, so Poisson's ratio and longitudinal strain here. So what is that answer here? Delta of V by V is equal to 1 minus of 2 times of sigma into delta of L divided by L here. So now let me understand about that. So energy, so in case of that energy, we can consider that energy stored in case of the spring. So that energy stored in case of the spring is mathematical expression I need to consider. So energy stored per unit volume we will consider. So we will consider that energy stored in case of spring here. So let me consider that mathematical expression for energy stored in case of spring. Okay, so let me discuss about that. Some formulas related to energy stored in case of a spring or stretched spring. Or potential energy we can call. So energy or potential energy stored in case of spring here. So we'll get that expression for that work done to stretch the spring. So that work done will store it as potential energy. Let me consider work done. That work done is stored it as a potential energy. So after deriving, we will get that expression. So 1 by 2 or half of F into E here. So look at here. What will be the mathematical expression for that potential energy of a stretched spring here? So half of F into E here. So look at here. So where F represents that force here, where E represents that elongation here. So what's that F term indicates here? F represents that force here, E represents that elongation, or we can call it as delta of L. So now we will consider that potential energy per unit volume. So potential energy, we got that potential energy. So I will find out that potential energy per unit volume. So potential energy per unit volume is, so U is equal to what? Half of F into E. Volume shall I write it as the area into length here? So did you get my point? So volume I can take it as, so area into length. So look at here, half of F by A here. So E by L. So F by A is nothing but what? So that is strain. So force per unit area. So F by A represents that stress here. So delta L by L is nothing but what? Change in length to that of original length. So that is strain here. So what will be the expression for that potential energy per unit volume here? Half of, so F by A is nothing but what? Stress here. Half of stress into strain. So what is that expression for that potential energy per unit volume here? Half of stress into strain. So I can rewrite here in one more form. So U is equal to 1 by 2 stress into strain here. So this is the formula. So we know that Y is equal to what? So Young's modulus, stress by strain here. So let me consider that strain here. So strain is equal to what? So let me take that strain is equal to stress divided by Young's modulus. So it means that, so wherever strain is there, shall I take that stress divided by Young's modulus? Then what will be this equation? So this equation becomes So stress, half of stress into, so strain means what? Strain I will take it as stress divided by Young's modulus. So half of stress into stress, stress square divided by Young's modulus. So what's the equation here? U is equal to half of stress square divided by Y. So where Y represents that Young's modulus R in this equation. So what about the stress here? So Y is equal to stress by strain. Let me take that stress value. So stress is equal to what? Y into strain here. So again this equation I can rewrite in another form, half of, so stress is nothing but what? Y into strain, so into strain here. So R, U is equal to 1 by 2 Y into strain square. So this is all about potential energy stored in case of a spring. So what is that potential energy? Half of F into E. Potential energy per unit volume I will take. So potential energy per unit volume is, so half of stress into strain. So this equation I can rewrite in terms of stress and I can rewrite in terms of strain here. So this is about mechanical properties of solid here. Okay, so we'll look at some numericals related to mechanical properties of solid here. So I will read out the question. Two wires of the same materials and same mass here. So nature of the material is same and mass of the two bodies is also same, are stretched by the same force. Here force is also same. Their length are in the ratio 2:3. Their elongation are in the ratio is. So look at here. So they mention length are in the ratio 2:3. So in that question they mention, so what about that elongation in terms of ratio? So we know from that Young's modulus, so Y is equal to what? F into L divided by A into E. So for example, so multiply and divide by L to this equation. So for constant volume, so Y is equal to F into L square. Area into length means what? Volume into elongation. They mention that force is same material, so mass is same means volume is same. So elongation is directly proportional to square of its length. So already we know this equation. So E1 by E2 is equal to what? So L1 square divided by L2 square. Then what will be our answer? So L1 square means what? So 2 square 4, 3 square 9. Elongation in terms of ratio is, so 4. Okay, so we'll read out the next question here. A thin rod of negligible mass, area of cross section is 4 into 10 to the power of minus 6 meters square. So one metallic rod is there, it has negligible mass and its area is 4 into 10 to the power of minus 6 meters square, suspended vertically from one end. So look at here. So this is the nature. So this is one rigid supporter. For this rigid supporter I am hanging one metallic rod. It has negligible mass and that area is 4 into 10 to the power of minus 6 meters square. It is suspended vertically from its one end, has a length of 0.5 meter at 100 degrees Celsius. What's the length of this wire? Length of this wire is 0.5 meter when the temperature of this wire is 100 degrees Celsius. At 100 degrees Celsius, this is the length of the wire. The rod is cooled to 0 degrees Celsius. So temperature is reduced from that 100 degrees Celsius to 0 degrees Celsius, but prevent from the contrasting by attaching a mass at its lower end. So look at here. Initial temperature is 100 degrees Celsius. I am reducing the temperature from 100 to 0 degrees Celsius. Then what happens is, so this metallic rod is try to compress here. So in order to avoid that compression, so what I am doing here? So I am attaching certain kind of mass at its lower end. So I am attaching mass at its lower end. So I need to determine, so how much mass is suspended at its lower end in order to prevent its compression. And also they asked to determine that energy stored in the rod is. So two terms I need to find out here. So this question is related to thermal force. So from that Young's modulus. So y is equal to F into L divided by A into E here. So F is equal to, shall I take that y into A, E by L here. So look at here, F is equal to y into A. So already we discussed about these formula. So elongation is nothing but what? Delta L here. So alpha is equal to delta L by L into delta T. So this is the original formula for that coefficient of linear expansion. So delta L by L, alpha into delta T. So shall I take this one? Delta L by L is nothing but alpha into delta T. So F is equal to y into A into. So delta L by L is nothing but what? Alpha into delta T. So force, shall I take it as a mass into acceleration due to gravity? So this is the formula, y into A into alpha into delta T. So from that thermal force, F is nothing but a m into g, y into A into alpha into delta T. So I need to find out that m value here, y into A into alpha into delta T divided by g. So this is the formula. So let me substitute the values here. So look at here. So in that question they given y value, so 10 to the power of 11 Newton per meter square. Y value is how much in that given question? So 10 to the power of 11 Newton per meter square. Area value is how much? 4 into 10 to the power of minus 6. And alpha value is, so in that given question they mention alpha is 10 to the power of minus 5. So this is given thing, y value, alpha value and z value, and delta T. So delta T means change in temperature. So that is 100 minus 0. So that is 100 only. So 10 to the power of 2 divided by g. Acceleration due to gravity is 10 here. What's the value? 10 to the power of minus 6 into 10 to the power of minus 5. So 10 to the power of minus 11. 10 to the power of plus 11 and 10 to the power of minus 11 will get cancelled out here. So here this is 10 to the power of 1. 4 into 10 to the power of 2. So if it goes to numerator, 10 to the power of minus 1. So m is equal to what? So 40 kg here. How much mass I need to suspend at the lower end in order to avoid the compression here? 40 kg. So next one is, so which thing I need to find out here? Potential energy here. So what is the formula? Half of force into elongation. So but they didn't mention that elongation, prevent that elongation. So I am preventing that elongation, means energy stored per unit volume is, so that is half of F into E. So look at here, energy stored per unit volume, I will take it here. So half of F into E. So volume means I will take that. So look at here, U is equal to 1 by 2. So in case of that, so I will take that. So half of stress into strain I will take. So look at here, half of stress into strain here. So energy per unit volume. So I can take that half of stress into strain into volume. So volume, shall I take it as a area into length here? So they asked to determine that. So potential energy of this metallic rod. So volume I will take it as area into length here. So look at here. Stress is nothing but what? Force per unit area here. So what's that stress here? Force per unit area, m into g divided by a. Strain, so delta L by L here. So area into length. So substitute the value. Mass is 40 kg. Gravity value is, so 10. Area is 4 into 10 to the power of minus 6. So look at here. So delta L by L is nothing but what? Alpha into delta T. So alpha value is 10 to the power of minus 5. Delta T means 10 to the power of 2, 100 degrees Celsius. Area value is 4 into 10 to the power of minus 6. Length of this metallic rod. So that length of the metallic rod is 0.5 meter. So 4 into 10 to the power of minus 6 term will getting cancelled out here. 20 here. Sorry. So 20. So 0.5. So look at here. So 20 into. So 10 to the power of minus 5 plus 2. So 10 to the power of minus 3 here. So look at here. 10 to the power of 1. 10 to the power of minus 3 into 0.5. So 0.5 is nothing but what? So 1 by 2. So 10 here also. Energy is So 10 into 10 to the power of minus 2 here. So look at here. So 10 to the power of minus 1 joule or 0.1 joule. What is the answer here? So 0.1 joule here. So look at here. Energy stored in case of the wire is 0.1 joule here. So we'll look at next one. Work done in stretching the wire 0.1 millimeter is 4 joule here. So what is the length of the wire here? Length of the wire is 0.1 millimeter. So 10 to the power of minus 3 meter here. So in order to stretch the length of the wire 0.1 millimeter is 4 joule here. So work done will be 4 joule in order to stretch that 0.1 millimeter wire. Work done in stretching that other wire of same material here. So another wire we will take, that another wire having that same kind of material but double the radius and half of the length. So look at here, another wire having that radius double of the initial one and half of the double of the initial radius and half of the length here. Then what about the work done in joules here? So which thing I need to find out here? Work done in joules here. So what is the connecting formula here? Young's modulus, Y is equal to F into L divided by A into E. So same material dimension here. So same material dimension means, so I have to find out that force value here. So force value is nothing but what? Y into A into E divided by L here. So look at here, same material means Young's modulus value will be same here. So look at here, so I have to consider that elongation is also same. F is equal to what? A by L here. So F1 by F2 is equal to A1 by A2 into L2 by L1 here. So look at here, what is the equation I get it here? So force F is equal to what? So F is equal to A1 by A2 into L2 by L1. Area means pi r square here. So R1 square divided by R2 square into L2 by L1. R1 value is how much? R1 value is R, sorry, R1 square. R2 value is what? So 2R whole square or 4R1 square into L2 value is how much? L by 2. L1 value is L here. So R1 square term, L term will get cancelled out here. So F1 by F2 is equal to what? So look at here, F1 by F2, it is equal to what? So here 4 and here 2. So 1 by 4 into 1 by 2. So that is 1 by 8 here. So F1 by F2 is equal to what? 1 is to 8 here. So work done is nothing but what? Force into displacement. So that connecting formula, W1 by W2 is equal to 1 by 8. So force and work done, proportionality quantity. So W2 is equal to what? 8 into W1. So 8 times of, what is the work done in case of that 0.1 millimeter wire here? That work done is 4 joule here. So 32 joules here. What is the work done here? Work done on in case of that second wire is 32 joules here. So we'll look at that next question. The length of material wire is L1 here. So look at here, the length of a metal wire is L1 when tension in it is F1 here, so or T1. So look at here, I am having one wire here, that wire having that length L1 when tension T1 is applied or force F1 is applied. For force F1 its length is L1, and when tension F2 or T2 you can take, when tension T2 is applied then its length is L2. Then what about the natural length of the wire? So look at here, so this is one wire here, its length is L1 when tension T1 is applied, and when tension T2 is applied its length is L2 here. Then what is the original length? If you are not applying any kind of force, what was the original length of the wire? I need to find out here. So look at here, in order to get that one, elongation is directly proportional to force. So elongation is directly proportional to force or tension. So tension T1 is directly proportional to elongation. elongation is nothing but delta L. So L2 minus of L1. So look at here, if tension T1 is applied, elongation is E, or I can take this one as a delta L or T1. So delta L is nothing but what? L2 minus of L1. L2 means final length, L1 means initial length here. So initial length is L1 here in generally. L1 minus of L here, final minus of initial. Similarly, second wire, length L2 minus of L. So change in length to that of original length here, L2 minus of L here, and another one is L1 minus of L. So hope you understand. L means original length. If tension T1 is applied, its length is L1. If tension T2 is applied, its length is L2. If that tension or force is not applied, means what was the original length of the wire. So I will divide these two equations now. So T1 by T2 is equal to what? L1 minus of L divided by L2 minus of L. Make that cross multiplication. T1 into L2 minus of L, T2 into L1 minus of L here. T1 into L2 minus of T1 into L, T2 into L1 minus of T2 into L. So let me simplify this equation. Look at here, T1 into L2, T2 into L1, I will take it into left side, minus of T2 into L1. So look at here, minus T1 into L, if it goes right side, plus T1 into L, minus of T2 into L here. So in this equation, so T1 minus of T2, L I will take it as outside here, T1 into L2 minus of T2 into L1. So then L means original length. So T1 into L2 minus of T2 into L1 divided by T1 minus of T2. So this is the equation to determine the origin.